Hello everyone, my name is John Henry and joining me in this video is Mr. Adrian, and today we'll be discussing the bucket sort algorithm with you. So first, what is bucket sort? So bucket sort is a sorting algorithm that divides an array's elements into several buckets. It works by distributing the elements of an array to a number of buckets. So each bucket is then sorted individually, either using a different sorting algorithm or by recursively applying the bucket sort algorithm. So the key to understanding bucket sort is the divide and conquer strategy. So first thing you will do is divide the elements into certain buckets, then sort these individual buckets and conquer them to achieve the final results. So to further explain what bucket sort is, let's make a real world example on how this sorting algorithm works. Now for our step-by-step visualization of the bucket sort algorithm, let's imagine that you've ordered a package from China. As you can see on this map, it's quite journey for your package to make. It starts in China and travel across the sea before finally arriving in the Philippines. This is similar to having an unsorted list of elements in our bucket sort algorithm. Now, before your package can reach you, it first arrives at a central warehouse. This warehouse is like our main array where all elements are initially unsorted, and this is where the magic of sorting begins. So inside the warehouse, packages that is bound to different regions are scattered around, much like an unsorted array. So our task here is to sort this package based on their destination region and using the bucket sort algorithm. Now, each package is assigned to a bucket, or in this case, a box labeled with region. So for example, if your package is addressed to Davao City, it goes into the region 11 box or bucket. This is the divide part of our divide and conquer approach, where we divide our problem into smaller and more manageable parts. Now comes the conquer part. Each bucket is sorted individually. This is much easier as each bucket has fewer package than the total and all belong to the same region. So as we know, Digo City belongs to region 11, and Jensan is to region 12, Dipolog to region 9, Iligan is region 10, as well as the CDO, and Butuan to region 13, and Davao City, of course, belong to region 11, and finally, Cotabato belong to region 12. So within each original bucket, packages are further sorted based on their zip codes or city names. For instance, in the Region 11 bucket, Davao City comes first before Digos when sorted alphabetically. This is like sorting elements within individual package in our algorithm. Now, with all packages are sorted and organized in their respective buckets, they are ready to be dispatched across the country. From the central warehouse in NCR, they embark on their final journey. So it goes to Mindanao, and a delivery truck loaded with a sorted package from the warehouse sets off on its route. This represents the process of merging all sorted buckets into a single sorted array in our algorithm. And finally, your package arrives at your doorstep from its origin in China to its final destination at your home in the Philippines. So it's been sorted and delivered efficiently thanks to a process much like the bucket sort algorithm.
Now, let's discuss the time complexity of bucket sort and compare it to other sorting algorithms. Here are the best case, average case, and worst case time complexity of bucket sort, as well as its space complexity. The worst case and average case time complexities are the same because bucket sort's performance largely depends on the distribution of the input data. The best case time complexity and space complexity are both considered the same because the best case scenario for bucket sort occurs when elements are uniformly distributed across the buckets. Bucket sort is known for its efficiency when dealing with a large range of input data, especially when elements are evenly distributed across the buckets. In the best case scenario, where elements are uniformly distributed, bucket sort performs exceptionally well with a time complexity of O n plus k, where k represents the number of buckets. This makes it highly efficient for such cases. Now, let's briefly compare bucket sort's efficiency to other sorting algorithms. Here is the CompSort average case time complexity, where p is the number of increments. This scenario is more comparable to bucket sort's best case performance when elements are uniformly distributed. Here is the counting sort time complexity. Similar to bucket sort's best case scenario, however, it's most efficient when the range of input values is small. Here is the merge sort time complexity, making it efficient for general cases but potentially slower than the bucket sort in scenarios where elements are evenly distributed. Here is the quicksort time complexity. In the worst case, it can be less efficient than bucket sort's best case performance. However, it usually performs very well in practice due to its efficient partitioning and randomness when choosing pivots. Here is the radix sort time complexity, where k is the number of digits in the maximum number. It's efficient when k is small, but it may be less efficient than bucket sort for larger k values. Here is the shell sort worst case time complexity, which can be less efficient for highly unsorted data, and may not be as efficient as bucket sort for certain scenarios. In summary, bucket sort's efficiency shines when dealing with uniformly distributed data due to its impressive best case time complexity of O n plus k. While other sorting algorithms have their strengths in different scenarios, bucket sort's performance in such cases makes it a valuable tool for specific sorting tasks. It's essential to choose the right sorting algorithm based on the characteristics of your data to achieve optimal sorting performance. Here is the Java implementation of bucket sort. The bucket sort method takes in two parameters: array, which is the input array to be sorted, and numBuckets, which is the number of buckets to be used for sorting. The code first checks if the array is null, empty, or if the numBuckets is less than or equal to 0. If any of these conditions are met, the method returns early without performing any sorting. The code initializes min value and max value to the first elements of the array. It then iterates over the remaining elements of the array, updating min value and max value, and if the smaller or larger value is found respectively. The code calculates the bucket size by dividing the range of values, max value minus min value, by the number of buckets and adding 1. This ensures that the range is evenly divided among the buckets. The code creates a list of buckets using the ArrayList class. The number of buckets is determined by the numBuckets parameter. Each bucket is represented by an array list. The code iterates over each element of the array and calculates the bucket index for each element by subtracting the min value and dividing by the bucket size. It then adds the element to the responding bucket using the add method of the array list. The code iterates over each bucket and sorts it using the collection sort method. This ensures that the elements within each bucket are sorted. The code combines the sorted bucket back to its original array. It uses two nested loops to iterate over each bucket and its elements, assigning them to the appropriate position in the array. The main method demonstrates the usage of the bucket sort method. It creates an input array and specifies the numBuckets parameter. It then calls the bucket sort method, passing in the array and numBuckets. Finally, it prints the original array before sorting, and the sorted array after sorting. In conclusion, bucket sort is a divide and conquer sorting algorithm that can be efficient for specific scenarios, but its performance depends on the distribution of input data. It's essential to choose the right sorting algorithm based on the characteristics of your data to achieve optimal sorting performance.